Alright, so I think this is recording. Sometimes I can never tell. Let's take a look at some of these uniform motion problems. We're either going to use that distance is equal to rate times time, or time is equal to distance divided by rate, or if we have the total is the sum of the parts type of idea, that the total distance is equal to the distance of leg 1 of the journey plus the distance of leg 2 of the journey plus the distance of leg 3 and so on, or that the total time is the time of leg 1 of the journey plus the time spent on leg 2 of the journey plus so forth. Alright, so let's take a look at number 1. During Indianapolis 500, let's see this car number 18 traveled 200 laps, which is 500 miles, in the same amount of time that it takes the number 12 car to travel 495 miles. So the car number 18 was the winner. It traveled further in the same amount of time. It completed the 500-mile race in first place. And it doesn't say whether this is second place or not, but it's definitely after the first place. So the one that won the race, the car number 12, traveled 1.8 miles per hour faster than the number 12 car. Find the rate of each car. Alright, so it tells us in the same amount of time. So we're going to take a look at the time that the number 18 car was driving on the track. And we're going to set it equal to the length of time that the car that number 12 was driving on the track. And we know that time is distance divided by rate. So we're going to try and find information in the problem about the number 18 car and come in and try to find distance and rate, that information about the number 12 car. So the distance that the number 18 car traveled, it told us was 500 miles. And the distance that the car number 12 traveled wasn't as much, it was 495 miles. And see, the time was the same, so that's why those are equal. That's why we have this equality. The rate. The car number 18 was traveling faster. So if we let x be the rate of car number 12, car number 18 was faster. So we have to add, and it tells us that it was 1.8 miles per hour faster. So now we have one equation and one unknown, and we can solve for this. So typically the hardest part of the problem is over, and solving this equation is a proportion, and you've done that before. We're going to multiply, we're going to cross multiply along that diagonal, multiply along this diagonal, and when we get x, now it wants the rate of each car. We're going to find the rate of the number 12 car, and then we'll add 1.8 to it for the number 18 car. So if we cross multiply along the gray diagonal, I get 500 times x, and along the yellow diagonal, I get 495 times x times the quantity, x plus 1.8. So let's come in and let's take 495. Multiply it by 1.8. 891. Divided by 5. 100 178.2. That's miles per hour. Hey, that's the slow car, the number 12 car. If we add 1.8 miles per hour to that, that'll give us the rate of the faster car. The 0.8 will bring us up to 179, and then this will be 180. So this 178.2 was the number 12 car. $180 was the number 18 car. If we check those answers against the key that's on the website, yeah, we've got the number 18 car is the rate of it is the speed of it is 180 miles per hour, and the rate of the number 12 car is 178.2. So that's the same answers that we just got, which is a good thing. All right. Mike is training for a marathon. So he begins running at a rate of 6 miles per hour 1.5 hours after Mike leaves. His friend Larry begins riding a bicycle at a faster rate, at a rate of 18 miles per hour. How long after Larry leaves will he catch up with Mike? So how long does it take Larry to catch up to him? We know that Mike had a head start of an hour and a half. And when Larry has caught up to him, then they have each traveled the same distance, not in the same amount of time, because with Larry riding the bike and going so much faster, why he covered the same distance in a lot less time. How far have they both traveled? All right, so if they any time that you're catching up to somebody and you've started from the same place, and when you caught up to them, you're both together, you've traveled the same distance. So we have the distance that Mike has ran is going to be equivalent to the distance that Larry has ridden his bike. Now distance is equal to rate times time. So we'll take the rate of Mike times the length of time that Mike has been running, and we'll set that equal to the rate that Larry rides his bike times the length of time that Larry has been riding. See if we can get a relationship from this. So we know Mike's rate, that he's running at 6 miles per hour. And we know Larry's rate, he's riding his bike, he's pedaling at 18 miles per hour. Now, I don't know how long each one has ridden their bike or how long they've run. So if I let X be Larry's time, I know that Mike had a head start. He's been running longer than Larry has been riding, because he took off an hour and a half ahead. So I know that I can say X plus, oops, that's multiplication, that it's X plus an hour and a half, 1.5 hours. Alright, so one equation and one unknown. So we've got 6x, and 6 times 1.5 should be 9. We'll double check in a minute on that. Subtract 6x from both sides. Divide by 12. That reduces to 3/4 of an hour, or 45 minutes, right? 3/4 of an hour. I don't know whether somebody would convert it to minutes or not, but a lot of times if it's less than an hour, they will convert it to minutes. Now, that was Larry. That's how long it took Larry to leave the house, to leave, well, wherever he was, I say leave the house, to leave and then to catch up to Mike. So on the first part, how long after Larry leaves will he catch up to Mike? 45 minutes later, or 3/4 of an hour later, Larry has caught up to Mike. Now, if we take this 3/4 and plug it into either side, because either side gives us the distance, let's just take 18 times this 3/4, and this will give me the distance. So 18 and 4 share a common factor of 2, and 9 times 3 is 27. Half of 27 is 13.5, right? Because 13 and 13 is 26, and 0.5 and 0.5 is 1. So, and this is the distance, which was in miles. So, if Mike takes off running, and he's ran for an hour and a half, and then then Larry jumps on his bike, it'll take Larry an additional 45 minutes to catch up to Mike, who and both of them at that point, when Larry's caught up, they've both traveled the same distance, which is 13.5 miles. Let's see if that's the same answers that we have on the key. Yeah, and it's even in minutes. It's not 3/4 of an hour. Either one, it's okay to write 3/4 of an hour. Actually, I'm surprised I didn't have that. We have 2 rental cars leaving the airport at the same time. One car is traveling east and the other is west. So they're traveling in the exact opposite direction, a straight line distance between the two. The car that's traveling west, the other car travels west at faster, 8 miles per hour faster. 2 hours after they take off from this same airport, they're 176 miles from each other. But obviously the one that's going faster has covered, more miles than the car that traveled slower. What's the speed of each car? So I have 2 approaches. We know that they've both been traveling for 2 hours, a length of time. So I could take the car that's traveling east, take the time that it's on the road and set it equal to the time that the car is traveling west, because we know that that would equal 2. But I don't believe that that's... I think what we should use probably is the 176 miles apart. So the total distance, that each car has traveled, well, part of that total came from the eastbound car. And there's no overlap if one's traveling east and one's traveling west, and they left at the same point, at the same place. So I have these 2 parts that add up to the total. Alright. That total on the left-hand side is 176 miles. Now on the right-hand side, I need the car that is traveling to the east and the rate of the car that's traveling to the west. I need the time that the east car is on the road and the time that the west car is on the road, the car that was traveling west. So I've got 176 is equal to, well, I know that they travel for the same amount of time, and that's 2 hours. Now, I don't know their rates. I do know that the car that travels east, and the other car, the west car, is the faster car. So if I call the rate east, west is the faster car, so I would add 8 miles per hour. Had I called the faster car X, then the slower car would have been X minus 8. And like I say, they've both been in 2 hours. They're 176 miles apart. So there's our equation. So once you get to that equation, you're home free. The rest of the problem typically is not that difficult. Not always, but most of the time. If I subtract 16 from each side, if I divide by 4, I have that the eastbound car is traveling at a rate of 40 miles per hour. And the other car is traveling faster, the westbound car. It says the other car travels west at a speed that's 8 miles an hour faster. So if we add 8, the westbound. So let's check and see if that's the same answers that I have on that answer key. It should be. Eastbound car is 40 miles per hour. Eastbound car 40 miles per hour. And the westbound car is traveling 48 miles per hour. So hey, we got the same answers that I had on that answer key. Let's take a look now at number 4. We have the Jones family. And they're going on vacation. And they have traveled 495 miles on their vacation. Their travels concluded driving over roads that had no construction, and they probably were averaging faster speeds during that no construction, so 60 miles per hour. And then on the construction area, you've got to slow down legally, and plus there might be traffic congestion, and the average speed is significantly slower, 30 miles per hour. They spend 5 times longer outside of the construction. So even though they're spending 30 miles per hour is the rate, and you're going a lot slower than when you're double your speed when you're outside the construction zone. You spent a longer amount of time, in fact 5 times longer, outside of the zones. That's good. How long does it take for the entire trip? So by how long, how much time does it take you to travel the 495 miles? Alright, so I have this total distance that is broken into 2 parts. The distance where you're driving through construction, and the distance that, no construction, just normal no construction. So the total distance was 495 miles. And distance is rate times time. So the rate when they were traveling through the construction times the time and the rate times the time under the no construction. So through the construction, their rate was slowed down. It was 30 miles per hour. But when there was no, they doubled that speed. Boy, they went 60 miles per hour. They spent 5 times longer outside of the construction. So if we let X be the time that was in the construction, then 5 times X, they spent 5 times longer outside of the construction. So one equation and one unknown, and we have to solve this. So I've got 495 is equal to 30x plus 300. So x is 495 divided by 3, I almost said 600. 300 plus 30 is 330. Alright, let's use my calculator. I laid my pen on top of my wireless tablet, so my mouse and my pen were duking it out for control. .5. Now that X represented the time. This was in hours, and this was in the construction zone. We want the length of the entire trip, so 5 times that. Seven and a half hours, right? Five times that. Is the hours, normal, no construction. How long does the entire trip take? 1.5 plus 7.5, 9 hours. The entire trip. 9 hours. Let's see if that's the same as my key. 1.5 through construction, that's what we had. 1.5 through construction, 7.5 outside of the construction, in normal driving, the entire trip took 9 hours, and that's what we have, is that this entire trip took 9 hours. Alright, so let's take a look at this one. And then I might stop it and call this part 1, and then continue with part 2 and make the rest of it tomorrow morning. Alright, so we have Sarah and Jenny, and it looks like they are in a race, but Sarah is much faster. She can run at 12 feet per second, and Jenny can only cover 9 feet in 1 second. So Sarah is going to give Jenny a head start. How many feet of a head start should Jenny give Sarah so that they both finish a 600-foot race at the same time? So they're both crossing the finish line. So here's the end of the 600-foot race. Now, way back here at the starting line, Sarah knew she was going to win. So while Sarah is at this original starting line, she gave Jenny, well, it's asking us how many feet should she give, so that if Jenny starts here, that if they're both racing, they finish at the same time. So with that head start, they have not run the same distance. But if we more or less Jenna's start, or Jenny's start, I changed her name. Jenny's start is here, so, and then she starts running. So they both start at the same time. So they have ran for the same length of time, but they have not covered the same distance. So let's set the times equal to each other. Because even though they're catching up, the head start was in terms of a distance, not in terms of time. So the time that Sarah ran is the same length of time that Jenny ran. Now if we assume, so really, I mean, her head start, she doesn't have to run full blast to get to that mark, to get to her starting point. I mean, she doesn't want to spend a lot of energy, so she could basically walk there. But when she gets there, that's her start. Sarah's start is here. They go, and they take off running. And when they're here at 600 feet, both of them are crossing that finish line at the same time is what the problem. So we want to know how much of a head start does Jenny get. So we know that time is distance divided by rate. For each lady. So here for Sarah, here for Jenny. Well, we know if it's a 600-foot race, and Sarah, being the faster, Sarah ran the whole 600 feet. Now Jenny, she ran less than 600 feet because Sarah said, hey, go up there and you start the race from there to make it fair. So she didn't run the entire, she ran this part that was her head start, she didn't run, so we'll take that away from that distance of the race there. So that's the length of her race. Now the rate of Sarah is 12 feet per second, and for Jenny it's slower at 9 feet per second. So now we have one equation, one unknown, and our x variable is the head start. X is Jenny's head start, and that's in feet. So if we cross multiply, then since we have a proportion, we have this diagonal and this diagonal. So 9 times 600, 9 times 6, 54, add the 2 zeros. 6 times 12 is 72, add the 2 zeros, distribute the 12 to minus 12x. So you're probably yelling at me that I didn't get in those zeros, right? So I'm getting that she should be given a 150-foot head start. So, like I say, she doesn't run the full 600. She runs only 450 feet because 450 plus the 150 is 600. So that's that's Jenny's head start. So some type of a summary of that. $150. So Sarah should give Jenny a 150 head start so that Sarah catches her 600 feet from the starting line. And that starting line we're talking about being the original starting line of the race, not Jenna's new, not her new starting line after giving that head start. All right. Well, I'm going to pause it there, get in here in the morning and do the rest, but this should give you some things to look at tonight. So I will talk to you tomorrow.